Thank you very much. So yeah, hello everyone, and thank you for coming. So first, a few words about the company. I will talk about few words about the company. So the company develops two products, SAR Investigate and SAR Federate. SAR Investigate is a web application which supports the task of investigative intelligence, and it is based on Elasticsearch and SAR Federate. It is used by different law enforcement and national security departments worldwide. So first, I need to put into context in which the SAR Investigate platform is used in order to understand what drove the development of the SAR Federate plugin. So SAR Investigate is facing different data challenges. It has to support different kinds of users. For example, it can be a police or a law agency. It can be some corporate. Then those users want to analyze different kinds of data. It can be unstructured data, like what you would find on the web. It can be semi-structured data, like the logs of an application. And finally, it can be structured data, like the financial records of a company. Then those users want to investigate different kinds of threats. For example, for the police, it can be to find cases of human or good trafficking. For corporate, it can be to understand if their product is used in any way to launder money. So the task of investigative intelligence is better described using this diagram. So first, a user has to identify the problem that he wants to investigate. Then, by exploring the data associated with that problem, the user is able to understand what is in the data, what are the important fields, how documents are interconnected. And by building this cognitive data model, the user is able to formulate better the query that he used at the beginning to identify the problem. And by evaluating the results that he got back, he can find, for example, additional problems related to the initial one that are worth looking into. So in light of the previous slide, a system that supports the task of investigative intelligence must be flexible in integrating and exploring different kinds of data. Also, the system must be highly performant in order to not impede the discovery process. Indeed, that discovery process is very interactive, and it doesn't work if the user has to wait 5 minutes each time to get a response to a request. So current information retrieval systems are very good at supporting the task of full-text search and also at analyzing numerical data. However, they lack rational and graph capabilities. These capabilities are crucial when analyzing the kind of data that users of the SAR Investigate platform are interested in. So in this picture comes SAR Federate because it brings rational capabilities to information retrieval systems. So in today's talk, I will present you first some joint queries. Then I will present some of the challenges in implementing rational capabilities over an information retrieval system. And I will finish by presenting you different internal aspects of the SAR Federate plugin. First, I need to give you some basic concept of the SAR Federate plugin. So when you want to join two indices, index A with index B, we'll say that index A is the parent index or the parent search, depending on the context. And index B is the child index or the child search. I will use a Venn diagram in order to illustrate the logic behind expressing a join with SAR Federate. So first, you need to define the search over the parent index. Next, a search over the child index. And their intersection will be defined by the join condition. Therefore, the response of the join will be the subset of documents from the parent index that have fulfilled that condition. So now I will present you a series of queries and benchmarks in order to show you the different capabilities of the SAR Federate plugin. Displayed on the screen here is... Oh, OK. So 1 second. Turn on laser. Yeah. So displayed on the screen here is a request that used the Elasticsearch query language. And SAR Federate has extended this language in order to introduce a custom query called join. So in light of the previous slide, you must first define the search of the parent. So here, this is done over the positions indices, and it has two filters, the geo-bounding box and the range query over a date field. Next, you have to define the child search. It is here again over the positions indices, but it could have been over any other index in the cluster. The exact set of filters that you use are omitted for readability purposes, but they are very similar to the previous two I have shown here. The only difference is that the range query is over a different time period. Finally, the join condition here is an equality between two fields, geotime hash from the parent index and geotime hash, again, from the child index. So that request is defined over an artificially created dataset of phone locations within a given area for a fixed time frame. This kind of request is typical for users of the Siren Investigate platform. For example, a user may want to analyze phone records that occurred in a given location, but at different time intervals. So I have executed this request in an Elasticsearch cluster containing 12 data nodes and 15 billion documents. The join itself processes 140 million documents on each side of the join. And on the right side of the screen here, I report the 90th percentile of the runs. So that request took 1.9 seconds. So you may be surprised at the time it took, but you have to realize that you are joining 140 million documents, which is quite a lot. And this benchmark has been designed to push the Siren Federate to its limits. But in that setup, you can achieve sub-second response time if you join about 80 million documents in each side. I will use that request as a baseline for the next queries I will present you. So the other query I want to present is again a semi-join. It's a semi-join. And the semi-join, as I didn't say earlier, but the semi-join is a type of join where you get only information from the parent index. Yeah? So here it is a semi-join coupled with an Elasticsearch feature called runtime field. So a runtime field is a field that you declare at query time. In this request here, I have declared two runtime fields, one for the parent index and the other one for the child search. I have updated the join condition to be defined over the runtime fields that I have declared. So that request took 1 second more than the baseline. The reason is the added cost of executing the script for each document that you have to process when evaluating the join. The other query I want to present is an inner join coupled with an aggregation. So with Siren Federate, it is possible to get information from the child index. So in order to do this, you have to project a field from the child index, and you have to use the project query clause on the child search here, and you will project the field MSISDN, for example. That projected field is made available on the parent context. So for example, here I can create an aggregation that will count the unique values of the projected field MSISDN. So here, that request took much longer, 7.7 seconds. The reason for that is the computation of the inner join itself. Indeed, it is very costly to compute the Cartesian product between the parent search and the child search. The other query I want to present is again a semi-join, but this time coupled with a runtime field of type lookup. So the lookup runtime field is a feature from Elasticsearch, which allows you to get information from another index. So for example, here, you want to get information from the person index and retrieve the first name and last name fields. The relationship between the current indices positions and the target index person is made through these fields here, MSISDN, that you have to declare in the runtime field. Then you can you can show the result of this lookup as part of the search response using the fields clause of the request. So on the right side of the screen now, you have the same request, but using only features from Elasticsearch, from Siren Federate. So in order to do that, the same query, but only with Siren Federate, you have to use explicitly two joins. On the bottom with the dashed line is the semi-join that I have been using so far. And above it, in the solid box, you have the inner join against the person index, through which you get the first name and last name fields. Then you will use again the field clause of the request in order to show the result of this projection as part of the search response. So I have executed these two requests 4 times, each time with a different number of documents being returned. So I have returned 10 documents, 100, 1,000, and finally 10,000 documents. So here, the requests that use the lookup runtime field from Elasticsearch are much faster than the requests that use only sign federate, the inner join. The reason for that is that the lookup runtime field is much lighter to compute. Indeed, it is only computed over the top K documents that you have to return as part of the search response. This is actually a core difference between the two approaches. You cannot create aggregations or queries over a field of type lookup. However, you can do these operations over a field that you project with sign federate. The 6th and final query that I want to present is a query that shows some graph analytics capabilities. So here, once again, I use the project query clause in order to get the MSISDN values from the child index. And then I create, on the parent search, a runtime field that will count the number of MSISDN values that you have projected that are related to the parent document. Then I create a range query over this runtime field. So in effect here, this query will return you the subset of documents from the parent index, which are associated with at least 2 documents on the child index. So here you can see that you have access to the graph structure of the data when you have to express your information need. Now I will present some of the challenges that appear when you have to implement relational capabilities inside the information neutral system. So when you want to join indices, you have 2 broad approaches. Either you can do it at index time, or you can do it at query time. Elasticsearch provides a few ways to do it at index time. For example, the enrich ingest processor or the parent-child join. These two solutions are based on the same concept. Whenever you index a document, you have to index in the same shard any related documents. The consequence is that at query time, you can achieve very fast search time. However, you have to pay for it with larger indices and costly data updates. So here, a data update is costly because each time you update a document, you need to re-index everything. So sign federate took the other approach of computing the join at query time. So in this approach, there is no extra cost related to data updates nor to the index size. However, there is a search penalty that you have to pay due to the need of exchanging data between nodes of the cluster. This penalty is attenuated thanks to a query planning and to various performance optimizations. So when you want to implement relational capabilities inside such an information neutral system, you need to bridge the gap between two data models. So you have on one side the document-centric data model, which is a model of information neutral systems, and on the other side, you have the data model of systems that are traditionally support the join capability. So on the document-centric side, you query for a document and you retrieve a set of documents. This means that the unit of information that you have to process is fixed. It is a document. Now contrast this against the relational data model, where you query for a row and you retrieve a table. Here, the unit of information is variable because a row indeed can be built from any number of tables. So this gap between the two data models has to be bridged over at different levels of the joint computation. So when you have to write the query, when you have to give the answer back to the user. So in Silent Federate, I will present you now how we represent logically a join. This logical representation is used throughout the query planner. So when you want to join these two indices, we first have two searches over the parent and child indices. Here you are on the document-centric model of the join computation. Then you have to join the set of documents that you have retrieved. Here you went into the rational model of the computation. Once you have the result of that join, you need to communicate it back to the system. So in effect, you need to jump back into the document-centric model. And here you need an additional filter over the parent index. Now I will present some of the internals of the Silent Federate plugin. First, I will give an overview of the different features of Silent Federate. So Silent Federate supports different types of joins. The semi-join is a core operation because it's quite interesting. Its complexity is linear with the size of the parent search. And also, the semi-join can be cached very efficiently into a bit set, which means that when the join has been computed, it is as costly to evaluate as a simpleton query. I will go into further detail later on this. And also, Silent Federate supports different kinds of join strategies, which are used depending on the amount of documents that you want to join together. So now I want to present you one of the join strategies that are supported by Silent Federate, which is the strategy where you partition the data over the cluster using a hash function. So on the left side of the screen, you have the logical representation of the join that I have introduced earlier. I will use it in order to support the example. And on the right side of the screen here, you have an Elasticsearch cluster with three data nodes. And the parent and child indices have three shards. So first, you need to execute the searches over the parent and child indices in order to retrieve the set of documents that you have to process in order to answer the join. Next, you have a hash partitioning function, which will be used to uniquely identify nodes in the cluster. Here, this is illustrated using color. Using this hash partitioning function, you will be able to associate a document with one of the nodes in the cluster. So for example, here, the document from the child index is associated with the green node, so on and so forth with the other documents that you have retrieved. The next step starts by exchanging data between nodes of the cluster. So this uses the hash partitioning function. The documents that were associated with a specific color will be sent to that node. So here, the green documents that will be sent to that green node, and so on and so forth with the other documents. Then you have to compute a join locally to each data node that has received data from throughout the cluster. I will explain this step further later on. But so once the join has been computed, you need to communicate the result back to Elasticsearch. So this is achieved by sending the subset of documents that were matching the join back to their originating shard. Then you have an additional filter which will read the result of that join and create a bit set. This bit set will be given to Elasticsearch in order to let it know what document in the shard is a match for the join query. So the other internal aspect of Silent Federate I want to present is the vectorization of the data processing. So in Silent Federate, we store data into OFIP. The rationale is to reduce the strain on the Java garbage collector. This data is stored using a columnar fashion in order to facilitate different kinds of operation over it. So in OFIP, you have vectors that represent fields in the data that you want to process. For example, the field that you are joining on, or the field that you want to project when you do an inner join. So there are two main ways to process this data. Either you process the data one row at a time, or you process it one column at a time. So here I will present you what happens when you process the data one row at a time. I will use these three layers: the application layer, the CPU cache layer, and finally the main memory layer. Here, the CPU cache layer is very simplified, but in practice, you have 2 levels or 3 levels of the CPU cache. Also, you have to remember that the application, when it reads from the CPU cache, it is much faster than when it reads from the main memory. So when you want to access this first element here in the first row of that column, blue column, what happens at the application level is that it will make a lookup into the cache. It is empty, so therefore you will have a cache miss. And then it will retrieve the relevant memory segment from the OFIP memory, from the main memory. Then this memory segment will be put into the CPU cache. Now, if you want to read this other element in the same row, but in another column, what happens at the application level is that it will be, again, a cache miss because the memory segment that is in the CPU cache is not the one that you have to read for that data. So now contrast this against the column-at-a-time processing. Here, I jump directly to the state of the application, where you have read the element from the main memory and populated the CPU cache with that memory segment. So now, if you want to read the next element in the column, here the application it will have a cache hit because the CPU cache has already the memory segment that you have to read. So in the past, Science Federate was using the row-at-a-time processing approach, but we have decided to use the column-at-a-time processing approach in order to leverage the CPU cache. So in order to facilitate the processing of columns in the code, we have introduced this pipeline abstraction over it, where you start with a tab. A tab is followed by one or more operator, and then you finish with a sink. The tab will read from the index, for example, and it will produce one or more batch. A batch contains a fixed number of rows, and these rows are stored into OFIP memory. Then these batch are sent to the different operators, which will scan columns, add a new column, remove one, whatever they need. Then the batch is given to the sink, which will be responsible in serializing that batch and sending it to whatever node in the cluster that requires it. So now I want to show you how we created the pipeline for the inner join that used the hash partitioning function. So this pipeline is executed when you have to evaluate the join locally on a data node. So on this data node, you have information from the parent index here on the left side of the screen, and you have information from the child index here on the right side of the screen. So we start by processing the data from the child index, and we create an hash table. Here, the key of the hash table will be the field from the child index that you want to join on. Associated with each key will be the ordinals to rows where this key occurred in. So for example, the key 1 occurred on those 3 rows of the child data. On the parent data, we have the following columns. You have the column where you want to join on from the parent index. There is also metadata, which is used to uniquely identify a document in the cluster. So the pipeline starts with this tab, where you have to scan the column from the field that you want to join on from the parent index. Then you will probe the hash table. If there is an entry in the hash table for that key, it means that the associated document is a match for the fulfills the join condition. So here, the first 2 documents have fulfilled the condition, but not the third one. So this tab outputted the following batch, which has 2 temporary columns. These columns have ordinals to the keys that were matching the join condition. Here you have to notice that the ordinals to the key 1 in the parent index are duplicated 3 times, and the ordinals to the key 3 in the parent index are duplicated twice. The reason for that is that the key 1 in the hash table was related to 3 rows, sorry, and key 3 was related to 2 rows. So in effect here, you compute the Cartesian product between the parent data and the child data. Then we have an operator which will read the ordinals from the column into the ordinals into the child data and retrieve the values at the indicated rows. So this operator is used, for example, when you have to project data from the child index, for example, the MSISDN field in the request at the beginning of the talk. The next operator that we apply is an operator that will read the ordinals into the parent data. And you will write down all the metadata that the parent data has. So here you write the doc metadata, the chart metadata, and finally the segment metadata. Next, the final step in the pipeline will be that sync, where I will read the chart column in order to know to which node of the cluster I have to send this row back to. So for example, the first 3 rows are associated with the same shard, number 1 here, so therefore they will be sent to the node X of the cluster. The final internal aspect of Silent Federate I want to present is the query cache. So it is possible to cache the result of a semi-join. The result is the subset of documents from the parent index, and therefore what you need to cache is a structure that allows you to encode this notion of subset. The bit set data structure is perfect for that, where you have an array of bytes, and the bit is equal to 1 if the document is inside the set, and 0 otherwise. Actually, this is what Lucene does. They use bit set in order to cache the result of queries. So when you want to make a lookup into this query cache, you need to compare the semantics between the query that you want to look up and the queries inside the cache. So we need to check if the 2 joint queries have the same parent and child searches, if they have the same condition, and finally, if the version of the searches are the same. So a version is computed by hashing the bit set of a search. We have written a patent that explains further this semantic caching of a join. Now I want to present the result of a benchmark. I will use the same benchmark that I have presented earlier of these phone locations, but this time I will use an Elasticsearch cluster with 36 data nodes. And I will benchmark 3 queries. Each query will join 2 sets of different sizes. So in the first query, each set will have 156 million documents. Second query, they will have 1 billion each. And finally, in the third query, they will have 2 billion documents each. Now, what I want to show you first is the evolution over time of the performance of Silent Federate plugin. So at the beginning, when Silent Federate was using the row at a time processing approach of the data, for example, the query tree, which is the largest in this scenario, was taking nearly 15 seconds. Then we have introduced the vectorization of the data processing, and we have seen significant performance improvement. We have run this Elasticsearch on the latest version of Elasticsearch and Silent Federate that is out, that was out this month, and we have seen a further improvement by at least 14%. Now I will focus on the benchmark that was run on the latest version of Elasticsearch and Federate. So the first query took 1.9 seconds. The second query took 5 seconds. This represents an increase by a factor of 7 in the amount of documents that you have to join together. And the runtime has increased by a factor of 2.6. The third query took 7.6 seconds, which represents an increase by a factor of 2 of the amount of documents that you have to join. and an increase by a factor of 1.5 of the runtime. So here we can see that Silent Federate is able to scale sublinearly with the amount of documents that you have to join together. To conclude this presentation, so I have shown you at the beginning different queries of Silent Federate coupled with Elasticsearch features. And with this, you can achieve very interesting, I think, query expressiveness. Also, I have presented you how the semi-join and inner-join indices work internally. And finally, we want to introduce different APIs. For example, a graph API that will allow you to do different graph metrics like centrality, an API for profiling requests with join queries. We are currently working on updated query planner, which will be able to select the most optimal join algorithm, regardless of the complexity of the request. And finally, we want to introduce a novel type of join, which is the spatial join. With this, you will be able to express a join over multiple dimensions. And with this, I conclude this talk. So thank you very much for listening. Yeah. Do you have any questions?
Thank you, Stefan. Very interesting and detailed talks. We have plenty of time for questions.
Is there?
Please always wait for the microphone. So. Thank you.
Hello. Thanks
Hello.
for the presentation. I was wondering, do you have a query rewriter, query optimizer module? How do you handle filters, for example, that are in the main query and that need to be pushed into one or other index? I mean, you need, like in databases, like in relational databases, somehow to rewrite the initial query to optimize the execution plan.
Yeah.
How does it work?
So yeah, we have a query planner, which will take the request that you have, and then we will figure out what filters have to be, for example, if you have to join index A with index B, we will figure out what filters have to be executed over index A, what filters have to be executed over index B. So then we will, I had this slide. Where was it? Yeah, this one, for example. So here you have the search with a set of filters that you have to apply on that index. You have another set of filters with the other search that you have to apply on the different index. So this is figured out by the query planner. Yeah. It will take care of whether or not you have to push down, whether or not you have to apply a filter on that index or not, because not all filters should be executed at this level. Yeah.
You've said that initially you were using row-based reads without hitting CPU cache, and you switched to column-based reads and started hitting the cache. What was the performance gain from this move?
So in this benchmark, we have seen at least twice as fast. I had the benchmark at the end. But yeah, from here to here, we have seen in this large-scale benchmark of 15 billion documents. You're not reading 15 billion, but at least in this benchmark, we have seen at least half of the time taken by the queries. So this was quite neat.
There was a gentleman behind you first.
Hi. I have a question about the columnar processing. You said that for cache efficiency, you use columnar representation for joins. I have a couple of questions around that. Are you using something like Arrow for columnar?
Yeah, we are using Arrow for simplifying the representation of data.
Intermediate representation.
Yeah.
Okay. And if you're using Arrow, then when you apply the filters, like the next level, so the first level document style filtering makes sense. then you do the hash join, and then during that phase you're converting everything to an in-memory arrow representation. Then you go back to the filter again, and there you mentioned that it's again like a document-based model for filtering.
Yeah.
So how does arrow map there to that? Like, but because it's still like a columnar filtering, right? Because it's an arrow.
Yeah.
If you convert it to document-based, which means there is a serialization, deserialization overhead.
Yeah. So for just the start, for people who don't know, Arrow is an Apache project which brings interesting representation of data in OFIP. Yeah. And yeah, so first, when you read data from the index, we populate this data into OFIP. Yeah. Then this is serialized. The vectors are the columns are serialized, sent to the nodes, and then we get the result back. And what happens is that we have a Lucene query, effectively, that will read the data that the node received. So the shard is in the one node. You send the result of the join back to this node. Then in that query, you will get the set of documents that were matching the join. And what you will do is that the Lucene query will read the subset of documents that you have stored there. So it will make like a lookup into this data, into this OFIP memory. And yeah, so this is integrated with the Lucene API, with this iterator-based API. So we will have, each time you will say, okay, this document is in the set, yes or no. Okay, let's go to it or skip it over.
Oh, I see. And what do you do when you map it back to Elasticsearch or Lucene? Is there you have to convert from the Lucene Arrow data structures again to the Lucene data structures? Is there a serialization, deserialization overhead there?
Sorry?
So let's say you computed the join and you got some results.
Yeah.
Then you return that results to the Elasticsearch API, right?
Yeah.
Is there a serialization, deserialization overhead there?
No, so the only serialization is between the net transport layer serialization, of course, when you have to send the data between nodes. But then what you have to create is this bit set data structure. So Lucene expects the bit set, and that's it. So this is on HIP, sorry. And there is no serialization happening between the two. You read, maybe in one aspect it could be serializing, but it's another representation of the data that you have off HIP as a bit set data structure that Lucene can understand.
Thank you.
I had a question about the code. How did you implement this? Because it seems like you integrate very closely with Elasticsearch. Did you have some challenges or to implement a plugin in Elasticsearch? Yeah,
so most of the challenges regards the search itself. So we need to kind of hook into different core aspects of Elasticsearch that is not internationally open, like the search service that you have to use to execute a search. We need to pass information to it in order to process the join. So this has to be customized, like you have with a reflection, for example, Java reflection. I think this is one of the most important one. For the inner join, recently we will update the code so that it uses runtime fields to facilitate the processing of the projected data. But in the past, there was no runtime field there when we did that, so we had to do a kind of a bit, not so ugly, but a bit hacky way of giving these unknown fields back to make these fields known to Elasticsearch. So each time there is a bit of, you have to go into these parts of Elasticsearch that are not essentially open, search service, the mapper service for extending, for adding new fields in the index, like when you have to project.
Thank you.
What about the licensing issues? Elasticsearch changed the license over the years, and if you're using part of it that in the X content and so on, are you facing challenges with this restriction?
No, so we just extend for example, like the search service. We just extend it. We don't add any other. We don't add new capabilities to it, or for also this part where we have to further, modify. We will put into a separate package, and we will see what to do with it. But yeah.
I think there are no more questions, and we
Thank you.
thank Stefan once again with an applause.
Thank you.